All right, this is the play posit on sliding friction. All right, so the first question is a baseball player is sliding into whatever base this is, going left. What is the direction of the force of friction between the dirt and the player? And what is the direction of that friction? Okay, so this is their velocity vector to the left, and I'm guessing that you can visualize it as they slide into home or whatever the first base, second base. They are running into all these little pieces of gravel, ouch, and that is making friction in this direction. So to help visualize even more, this is a website I really like, super readable. Let me know if you want me to make links to this. Ignore the person on the left for a minute. That's what we're going to do in person because it's more complicated. But stick person on the right is whenever your two surfaces are sliding over each other, you can visualize. I love that you can zoom in and see the nooks and the crannies are bumping across each other, and that's going to happen opposite the direction that they're trying to push it. Okay, so one more thing. The force of the person is this red vector, FA. The force of the friction is the blue vector, F sub F. In this case, they are equal because he or she or they are pushing it at a constant speed, but that's not a given. Person might be pushing with, if the red force was bigger, it'd be speeding up. If the blue force were bigger, it'd be slowing down. Okay, so that I wish that they hadn't done that, but anyway. So the force, nice visualization of the force. All right, so please write this down. The normal was always perpendicular to the surface because surfaces push. Friction is always parallel to the surface because as the one surface tries to slide over the other, you can see that there's a big glob on the floor that is pushing into the crate right here. So it's really a normal force. It's really thousands and millions of little normal forces. This crate's trying to slide across the floor. It runs into that. You got another normal that maybe is embedded, and you got a really strong normal. So all of these normals are going to be pushing opposite the direction of motion, which is this way. Okay, do not worry about the attempted motion. That's what we're going to talk about in class. But this is why I suggest draw the velocity vector off to the side. It's not a force. Friction will be opposite that. Okay, so please write that down. And there is a formula for sliding friction. Little kind of notes on the notation. Capital F stands for an arbitrary force that we haven't decided yet. So sigma F equals ma. That means I'm going to go decide what forces are acting. It could be any force, tension, weight, normal. Lowercase f is for friction. And in class, we're going to learn about static friction. So we're going to say K for kinetic. So maybe I don't love, some books will say sliding friction. It's probably better that you say kinetic to not be confused with static friction. Okay, so you need a subscript because there's two types of friction. This is the Greek letter mu. You have potentially seen it in terms of it meaning 10 to the minus 6. Okay, it does not mean 10 to the minus 6 here. What it means is roughly, yar, how rough these two surfaces are. I'm putting that in quotes because you could have really, really smooth surfaces like two glass plates for your biology, and they feel really smooth, but they actually have an incredibly large mu. So it's really more how interactive these two surfaces are. And I really do mean two surfaces. On the next page, we're going to look at a table of some sample values, but you can't just say, it's not like the density. You can't go look up and say, what is mu for wood, or what is mu for carbon, or what is mu for paper. You have to say, what is mu for waxed wood on wet snow, for a skier. You have to know the two surfaces. Okay, so generally you're either solving for this and it's the only thing you don't know, or the problem will tell you what the value of mu is. Okay, and it is called the coefficient of kinetic friction. So the problem we're going to do one single problem, asks us to solve for the coefficient of kinetic friction. Coefficient just means it's in front of the normal. Okay, and then the other thing that's going to determine friction is, so given how rough these two surfaces are, the other thing that's going to affect it is, this is the normal force. Because if I squish these surfaces together more, that's going to increase the normal, which is going to mean you can imagine this thing, the crate, digging deeper into the floor below it, which is going to make the resistance to getting over these nooks and crannies that much greater. All right, and so it ends up being more or less, at least for the type of problems we're doing, directly proportional. Okay, so this is the most fun, the most fun you're going to have in physics all year. Just kidding, you're going to have lots more fun. So that is the new formula. Friction is directly proportional to the normal times this coefficient of kinetic friction. Take a quick look at what some of those are. Again, ignore the middle column, that static friction we haven't learned yet, but Teflon, which is what they use for the non-stick pans, on steel has a very low coefficient of friction. Shoes on wood is going to be high. Look at that, like much bigger, because you're not going to slide very well. But shoes on ice, not so much, closer to Teflon on steel. Okay, so the bigger the value of mu, the more interaction you have, which means the more friction you're going to have. Okay, when you are doing problems, please check your work, unless you're talking about, and I'm not trying to be funny, tape or glue, or they have invented rubber that as it gets warm gets gooey and melty for race car drivers. But neglecting anything like that, your mu should be less than 1. And so if it's a well-vetted problem that somebody has triple checked, if you get a mu bigger than 1, check your work. All right, so let's do this problem. You have a 65 kilogram stunt woman sliding across the floor with an initial speed of 6.5, comes to rest after 35 meters. So I'm going to pause the video. You set up your whatever you need to find her deceleration, and then we'll check back. Okay, we really didn't care what time that happened, so most efficient way to do it, don't know, don't care. Hopefully you got negative 0.604. Check your work. The negative sign means that I'm being pushed by those nooks and crannies as she tries to slide along, opposite the direction she's going. So awesome. Make sure you have that value down, and then we're going to look at her forces. Okay, question B, draw a force diagram. We'll talk through this slowly because that's what's new, so we must never forget this. Does she have weight? Yes, everything has weight. Does she have a mechanical force? No. Some people, if you go back and think about, I know I still have them, but your pre-test, there was a question about like the force of her throw or the force of the hand, I think, on the pre-test on a baseball. She has inertia. She wants to keep going. She does no longer has a forward force, but she does have velocity. So keep that in mind. But there is no mechanical force. Her force, she threw herself or whatever on the floor, that's no longer there. Does she have a normal? Yes, because she's touching a surface. Does she have friction? Yes. Now we know how to draw friction. Opposite the velocity vector. Does she have tension? No, there's no rope. All right, and I deliberately chose this problem because I think initially people find it a little bit weird to be like, wait, friction must be fighting something. It's a reactive force. It is not reacting to other forces. It is reacting to the sliding of the surfaces, which is velocity. Okay, so again, I think sometimes people don't like this seems counter to, like, they don't like to be like, wait, how can I have friction when I don't have anything pushing me in the other direction? It's the nooks and crannies she's gonna bump over them whether she has a forward force or not, right? She's bumping over them not because she's being pushed in that direction. She's bumping over them because she has speed in that direction from a previous push in period 1. Okay, so that is the force diagram. Don't be afraid to just have friction. Okay, so checked, draw the force diagram. C, calculate the coefficient of friction, and that is a fancy way of saying find mu. So we're going to do, even though there's no angles, we need to look at the vertical column to find the normal force. So we're going to say that's a bad sigma. The sum of the forces equals 0 because she's not accelerating up and down. So normal minus mg equals 0. So normal equals mg. I know we can calculate these numbers. I don't want to because I want you to see that the mass cancels, but this is what I call a boring problem. Normal equals the weight. Okay, so after we do enough of those, if this is the case, you don't need to show all that work. Horizontally, do the sum of the forces equals 0 or ma. They have got to equal ma because there is a single force. It's unbalanced. You can't balance a single force. So again, what's a little bit disconcerting is that there's only that friction, it's just friction. Okay, if we want to talk about that in class, please let me know. You can imagine sliding like a tissue box across the floor. Your force isn't acting on it anymore. It's just the nooks and crannies. Okay, so only friction, and it's negative. What is friction equal to? It's the fun formula. What is the normal force equal to? In this case, it's ma, right? Not a lawnmower problem, not a suitcase problem, not an incline. So minus mu times, again, not g is positive 9.8. You don't want to hit minus sign in there. G is positive 9.8. But A, remember from our previous, you want to be consistent with those plus and minuses across, the different parts of the problem. A was negative, which is good because we never want mu. It's just a coefficient. Mu should not have sign or units. So mu is equal to 0.604 meters per second squared over 9.8 meters per second squared. Yay, it's dimensionless. 0.062. Okay, so even though you had her mass, do not worry if a problem doesn't give you mass. And I'll quickly talk about why that makes sense. As the mass goes up, her inertia goes up, and she wants to keep going forward with more intention. She has more inertia. But as her mass goes up, the weight goes up, which compresses the surface more, which makes the normal go up, which makes friction go up. Sorry, that's a little confusing because friction is pointing to the left, but friction's going to go up. So as the mass goes up, the inertia goes up, this side of the equation, but as the mass goes up, so does the pressure at the surface proportionally, so the mass cancels. All right, and I think that's a really important concept. Okay, so quickly, at 15 minutes, friction is opposite the velocity. Don't be afraid to just have friction. Make sure you feel comfortable with the terminology of the coefficient of friction. There's one new formula, the fun formula, and we will continue to practice this. All right, team, see you in class.